All right, good morning. My name is Greg Wadley with CTC and Associates. I'm the Clear Roads Administrator. We're here for an interim webinar, or excuse me, the final webinar with a project entitled Understanding the Salt Phase Diagram. This research effort is led by Laura Fay at Montana State University. Before I turn it over to Laura, I want to let everybody know that this webinar is being recorded. It'll be posted on the Clear Roads website at a later date for your viewing and you and your colleagues viewing. We also ask everybody stays on mute so that there's no background noise. However, if you have any comments or questions, please enter those into the chat box and we'll address them at the end of the presentation. So I guess that's it, and I'll turn it over to Laura.
Great, thank you, Greg. So this is the final report presentation for the Clear Roads project, Understanding the Salt Phase Diagram. Just below the title, you can see the website for all deliverables associated with the project. So before we jump into presenting the project, I'd like to acknowledge some folks involved with the project, including the Clear Roads project panel, as well as Greg at CTC and Associates and the research team. You can see that it was a pretty broad group of folks from each research organization. It was a very unique project involving both lab work to graphics and videography. So I really wanted to acknowledge everyone that was involved. So the primary objectives of this project were to develop materials to aid winter maintenance practitioners in making informed decisions about the use of road salts. And these key deliverables were a one-page fact sheet as well as an educational video. So we're actually going to open this presentation with the final products that were developed. So as you can see here, it's a screenshot of the one-page fact sheet. It's in PDF form on the website and you can access it. And you can see here that the top of the form really just explains what a phase diagram is and what the different parts of it mean, whereas the bottom half describe what this means in terms of winter maintenance operations and how this can inform you when you use road salts. The other key deliverable was the educational video titled Understanding the Salt Phase Diagram. This is about an 8-minute educational video that can be found on the Clear Roads website. I'm not going to play it now because we've had audio issues in the past with playing a video through these platforms, but please know that you can access this from the website. Oh. So additional work that was associated with this project that helped provide information to support the one-page fact sheet and the educational video included a very detailed literature review as well as 2 separate lab demonstration projects. One involved using a whole bunch of beakers, so we called it the beaker test, and the second was a friction or trafficking test. I'm going to go through those results now. So from the literature review, just a summary of the findings are that there are quite a few examples of phase diagrams in the published domain, but these often lack sufficient explanation. They're often created and tailored for either engineering or chemists, and so they're hard to then apply into the winter maintenance domain. We also found that there are many test methods that are used to assess de-icer performance that can be used to help make informed decisions when using road salts. And on that same note, de-icer application guidelines can be tweaked or modified based on this data that you capture from lab testing. The literature review is very extensive and it can be found in the final report, which is linked below. A large part of this project involved lab testing. So first I'll talk about the beaker test. The goal was to document the percent of ice that formed in different salt solutions. So we had salt solutions that varied from 21 to 28% by weight of aqueous solution or liquid content. And we tested this at various temperatures. So there were 9 different temperatures from 32 degrees all the way down to -6 degrees. And this was all done on MSU's campus and the cold labs. So here's just a summary of what the different test parameters look like. Again, so we have our brine or salt solution concentration. We designated each beaker in groups, so A through H, and what these were labeled as. And this is important as you read through the report and as you look through pictures, so you can quickly identify what sample you're looking at. So a summary of the results is presented here. And you can see on the vertical axes on the left, you have your temperature in Fahrenheit. And then on the horizontal axes at the top, you have your salt concentration and the designated label of A through H for each group of beakers. And what we summarized here is whether ice was formed, and that's in blue, or if salt precipitated out, and that's in this orangey tan. And essentially what you can see here is that salt and ice were not precipitating out or forming until much colder temperatures, but also at the higher salt solution concentrations, which is what you would expect to see. So what did this look like? One of the great outcomes of this was Neil was able to take a lot of wonderful pictures. So we have a lot of photo evidence essentially to show along with this. So what we see here is at test temperature 32 degrees, and you can just see what this looked like in some of these beakers. I'm going to scroll through these fairly quickly, but the detailed lab results again can be found in the final report. So again, here's 25 degrees. You can see what looks like a little bit of salt precipitating out. F, G, and H are the higher salt concentrations. So again, you would expect to see a little bit of salt precipitating out at these higher concentrations. Here we're at 20 degrees, and you can see these beakers have a lot more material at the bottom of them. And you can see here in this photo that there is some ice crystal formation. And this red arrow is actually pointing towards a bubble in the ice matrix, which I'll discuss more in a little bit. Here is 15 degrees. Again, the beakers look very interesting. You've got ice formation. You've got a lot going on at the bottoms, and then you can see the detailed higher resolution images of these ice crystals that were taken at this temperature. 10 degrees, very similar. Again, very interesting images of the beakers and high resolution images of the ice crystals that were formed. And then at 5 degrees, we have really interesting ice crystal formation and salt precipitation out at the higher concentrations. At some of the colder temperatures, unfortunately, ice crystals were not able to be captured through the filtration method due to partially the cold, but also the timing of how the salt played out in the lab. And here we have 0 degrees Fahrenheit. So we're fairly cold in the lab. You have a lot of ice crystal formation. And then again, these red arrows are pointing at bubbles that have formed in the ice matrix here. And the coldest temp, here we are again at -6. Again, we were not able to filter out and take images of these ice crystals, the higher resolution images, again, due to time and conditions in the lab that made it challenging. But what does this all mean? So for the ice crystals that we're able to filter out and collect, about 18% of the weight of solution ended up being ice crystal and or salt precipitation. So that was interesting, but the results are kind of all over the map. And I think a more detailed look would be useful if someone wanted to kind of move forward with using this data in a winter maintenance application. So what are the takeaways from the beaker test? Unfortunately, it was challenging, as all lab and field testing are. There was some limited data capture at certain temperatures in terms of being able to capture these ice crystals and capture the high resolution images of them. In the future, if this was done again, we would increase the time for ice crystal formation from what it was to from 10 minutes probably to 30 minutes. Again, because of the different time lengths, some of the ice crystals were very small, and so different filtration methods were used, and this may have led to some inconsistency. But overall, again, we're very happy with the images and how those came out, and we feel like they do help paint a picture for what is hopefully seen in the field can now be kind of shown image-wise in the lab. The general findings are that there is an optimal salt concentration range for winter maintenance operations, and that as temperatures decreased, ice formed in solutions. Ice crystal formation and salt precipitation was not observed in the lower concentration solutions, which is to be expected. So again, the takeaway is that more salt is not always better. We were able to capture a time-lapse video of ice formation and salt precipitation in the lab, and this is posted on a YouTube page, and there is a link to it in the final report, so you can access this as well. So this is just a nice visualization of kind of what this looks like over time in the lab. So the second part of the lab testing involved looking at pavement friction, or what we call the trafficking test. So the goal was to measure pavement friction following the application of salt brine at varying concentrations. So this was done on both concrete and asphalt pavements at the full range of the salt solutions that were also used in the beaker test, so 21 to 28%. The salt brines were applied as anti-icers, so directly to the pavement at about 45 gallons per lane mile. And this test was done at 15 degrees Fahrenheit. And what you can see here is the trafficking apparatus as well as the plowing apparatus. And essentially the trafficking machine runs the tires run across the bulk of the sample, but the middle part of the sample shown in green is where both tires pass. So most closely mimicking what is seen on the road. And then the plow device on the bottom right-hand side is used, and the force to plow the snow off the pavement is measured. So what we can see here are the concrete samples. Again, these are labeled so you can go back to the final report and see the C represents the salt concentration. And it's so again, C22 would be 22% NaCl. And so this is what the trafficked concrete looked like on the left. And then once the snow was plowed off, what that looked like. And here is what an example of the asphalt pavement looked like. Again, trafficked, so snow placed, and the tire run over the sample and then plowed off again. We were able to measure the friction on the pavement in two methods. Actually, we used that plowing device where we measured the force that was required to plow the snow off the road, and those results can be seen here. So we dragged the plow device across, and you can see that overall friction on the pavement is very good. And then once the salt brine solution was applied or application, you can see generally the friction values are in the same range. Once we put the snow on and compacted it, friction values dropped because you're measuring friction from that compacted snow surface. We trafficked the snow, so we ran the tires over it. And you can see here for some samples, friction was lower, and for some, friction was higher than the compacted. And then once the material was plowed off, and it's the kind of snowy residual on the pavement surface, we measured friction again, and that's what this plowed value is. So this is the pull test or that friction device, the plow device I showed you for the concrete sample, and this is what that data looks like for the asphalt. The interesting thing from this data set is that you would expect friction to improve once that snow is plowed off the road. But for both the asphalt and the concrete using this test method, that was not observed. So we had some concerns about this data. But simultaneously, we were also able to measure friction using a Taconic non-invasive friction device. So that was mounted on the trafficking machine and collecting data simultaneously. And what we saw from the Taconic, for example, with the concrete is, again, you start with very high, good friction on just the pavement, the bare pavement. Again, fairly high friction once that salt brine is applied. And then when it measures friction, once that snow is compacted on the pavement, you get a large drop in friction, which again, you would expect to see and we saw previously. Once that snow is trafficked or the tires have run over it, we see a very consistent friction value to the compacted. But then once that snow was plowed off the pavement, we do see an improvement in friction. So this is the concrete sample, and here is the asphalt sample. Again, you see that improvement in friction once that snow and ice has been plowed off. There are a couple of reasons we think the Taconic data maybe better represents what's being shown in the field, and that in part may have to do with the amount of data that was collected. With the pull test, it's an intensive test spatially because you have to physically remove the snow from the sample, and so we were only able to do that 3 times, so triplicates for each of those. Whereas the Taconic is measuring and collecting data every second across the entire sample. So there's just a much broader data set with that Taconic unit. And the interesting thing was there was a significant difference found in the plowed friction values between the concrete and the asphalt samples from the pull test and the Taconic data set. So there is some merit to doing this, but in the future, if the pull test was used, we would want to collect significantly more data, but the better way to do this might actually be one of the non-invasive sensors like a Taconic. Other key variables that were identified in this test were snow density and humidity, and this may be strictly due to the lab environment. A lot of this testing was done in the summer, and the warmer temps outside created wide ranges in humidity in the lab for the friction trafficking testing. So it makes sense that there was an impact there. And we have observed from other similar testing that snow density does appear to have a large impact. And so again, this is something that could be further investigated in the future. Overall, the ranking of highest to lowest friction based on pavement type is interesting in itself to look at, but the values are kind of opposite between concrete and asphalt. So there was no clear trend that you could say, asphalt at this salt concentration has the highest or lowest friction, unfortunately. So moving into the conclusions for this project, I think one of the great outcomes is that we found that salt phase diagrams are great information sources for studying the chemistry of salt brine or sodium chloride solutions, and they can provide key information on the eutectic points and solubility limits. Phase diagrams can be used in making informed decisions about de-isotype and blends that need to be used in the field, but specific phase diagrams would need to be created for each of those specific de-isotypes and blends. Results from the lab produce great images and videos of ice and salt crystal formation, and also potentially dihydrate salt in solution. We also found that these bubbles present in the ice crystals could potentially be filled with salt brine, and this may indicate that the solid phase of ice crystals and salt crystals is not pure, and phases can coexist, so liquids and solids together. And this kind of reinforces earlier work by folks in Norway that suggests that when ice forms in the presence of salt brine, it actually forms at a weaker ice. So in theory, it may be easier to break apart. And overall, the pavement friction following the application of salt brine at these different concentrations, there were a lot of influencing factors, including pavement type, the salt concentration used, the friction measurement technique, as well as snow density and humidity. So a lot of variables came into play here. One of the cool pieces of this that the Muid and Matt did in the lab were the high resolution images of these ice crystals. And throughout this process and throughout the literature review, we learned that there are even more advanced imaging techniques that could be used that could determine what percentage of that ice crystal is actually made up of different chemical solutions. And so that would be a really interesting piece of future work to look into, whether you're using Raman microscopy, scanning electron microscopy, or any of these other methods that are being used out there. So again, the final report, this webinar recording, the one-page fact sheet, and the educational video that were created will be posted to the ClearRoads website, which you can access here. And we will open this to any questions. Thank you very much.
So we don't have any questions or comments in the chat box, but if anybody does have any questions, they can just go ahead and ask Laura now. All right, hearing nothing. Laura, thank you very much for your time and for the research team's effort on this. We really appreciate it. Thank you so much.